Hi guys, hope all of us are doing great. I had promised in our previous video that we are going to do a video on boron, and this of course was on the group 3 elements, which the said of course are going to be displaying some unique characteristics of individual elements. Now in this particular case, we're going to look at the case of boron, and boron is a member of the group 3 elements, which is going to be exclusively displaying non-metallic character both in its physical and chemical properties. And this is going to be one of the unique characteristic which is going to contrast it with other elements of aluminium, gallium, indium, thallium, and perhaps those specific elements. Now in this specific discussion, then therefore we're going to look at boron and some of its compounds. And we're going to see that boron as an element is going to be displaying some unique characteristics in its specifically bonding, which we are going to look at an example. And of course, we're going to see that most of the elements which are going to form covalent bonds, as we had said, these are going to be obtaining the octet state, especially for the central atom. Now, in this particular case, the element of boron is going to be unique in a sense that it's going to be, of course, lacking this specific aspect of the octet of electrons about its central boron atom. And this, of course, is going to be giving it its unique properties of being strong or forming compounds of course, strong Lewis acid. Now, in this case, we shall look at this specific element, perhaps by giving it its configuration, so that we're going to appreciate from this specific description, which I've just given it in my previous statement in forms of a summary. Now, in this case, we're going to have the 2s2 and 2p1 electrons given as such. So the valence electrons are going to be giving us the 3 electrons of the s and p orbitals given as such. And of course, these are going to assist us in trying to perhaps do some of the arrangement during its bonding. Now, this is specific deficiency of electron, which I've mentioned in trying to obtain this octet of electrons about the central atom. Now, the deficiency is going to, as I said, relate to the formation of boron compounds, which are going to be strong Lewis acids. Strong Lewis acids, and we're going to look at the boron's hydrides in that specific case, so that we are able to see which are some of these specific tendencies of this particular element. Now, of course, we are going to see that the unique type of bond which I've mentioned is going to be uniquely occurring in boron hydrides. So this is going to be a combination of boron and hydrogen, which we're going to see in forming compounds. Now, some of the compounds which we're going to see being formed by borons are going to be intermediates, especially boron hydrides, which is going to be a compound which has not been, of course, isolated, but of course it's going to be existing as an intermediate. So this is going to be boron, which is a compound which, of course, in some of the reactions we are going to come across, it is an intermediate which has not been isolated as a stable compound. But we are going to have a stable compound which is going to be one of the simplest boron hydrides, which has been isolated as a stable compound, which is going to be given as this. Now we're going to see that from our study of the organic compounds, we have given a compound which is going to be appearing similar to this particular compound. But of course, we are going to use this specific example. This, of course, is a 10, and we're going to, of the alkane series, we're going to use this specific example to try and see what are some of the unique characteristics in terms of bonding, especially in the Lewis structure, which is going to be displayed by this particular hydride of boron. And therefore, it's going to give it its unique characteristic, which we had mentioned in our opening statement, as a non-metallic, as a compound that is as an element which is going to display non-metallic character, both in its physical and chemical properties. Now, to explain this specific structure which is going to be formed by these boron hydrides, I'm going to use perhaps this particular illustration, which is going to be assisting us explain this. So in order for us to form a Lewis structure for the compound, which we had mentioned, for instance, for the 10, we're going to require 14 electrons in this particular case in order to form these specific bonds. And in this particular case, of course, I can just mention that we're going to require this four for carbon. So for the 2 carbons, we're going to require 8. So we're going to have 8 plus 6 from the hydrogens, which are going to form 14 electrons for us to form a Lewis structure of this specific compound. Now for boron, we're going to see that this specific compound which we have mentioned, which is the simplest that has been isolated, we have given it a formula of B2H6. Now from the electronic configuration which are given, of course, of the shortened version, I'd say that this is going to be 2S2 and 2P1 electron. So we're going to see that basically boron is going to have 3 valence electron, and therefore these valence electrons are going to be 3 by 2, and then we're going to have the 6 hydrogen, 6 electrons from the hydrogen, which are going to be involved in bonding. So this is going to be forming a total of 12 electrons. Now for us to have a Lewis structure that is going to be similar to the first one, member of the alkane series, which we had given an analogous structure, we will require 14 electrons for us to obtain that one. Now in this case, we're going to see that these specific hydrogens are going to form a unique bond with the central atom of boron, which we had said. And of course, this is going to be giving it a unique structure, which is going to be different from the Lewis structure that we're going to expect from this member of the alkane series. Now we're going to see that in each of these specific boron atoms, we're going to have a structure. Perhaps I can just give it, so let's have this one. So we're going to have 12 electrons. So we're going to have boron at this specific point, and another atom at that particular point, and then we shall have hydrogens attaching to this specific boron atom. So we're going to have 4 hydrogens, and then the remaining 2 are going to be attached at this specific point. Now there's going to be a unique bond which is going to be formed at this particular junctions, which basically is going to form some kind of a bridge. So we shall have the boron hydrogen bonds being formed between these ones, and therefore they are going to be 4 in number. So these are going to be 4 bonds sharing a pair of electrons. Therefore we are going to expect that these ones are going to be involving 2 electrons per bond, and then we shall have 8 electrons being involved in formation of this first, so perhaps I give this one as such, first, second, and then we shall have third, fourth. Now there's going to be a bridge of the boron hydrogen and the boron bond, which is being formed in between this specific atom, this one and this one, and then we shall have another one forming to this one, this one, and this one. So we shall have 2 bonds of this specific nature. Now these bonds are going to be given a name referred to as the 3 center to electron bonds, which are going to be involving of course the remaining 4 electrons. So in this case, if we had 12 electrons from each specific bonding structure, the entire molecule, we're going to see that out of the 12 electrons, 8 are going to be used in formation of course, the boron hydrogen bonds, and of course the 2 center 2 electron bonds which are going to be formed are going to be shared among those specific 2 hydrogens and the 2 respective boron atoms. So therefore we are going to have a structure which is going to be appearing as such. So I use the various perhaps orbitals which are going to be involved in between for me to give an elaborate example for that one. So we shall have this one. So so drawing a Lewis structure, we're going to have 1 electron from boron being donated to form a bond with hydrogen, and then we shall have these respective bonds now forming using that specific example. So we are going to have similar bonds of the 4 which we had mentioned for this, forming this one. And then we shall have the 2 hydrogens forming bonds through sharing of those specific electrons. And therefore the 4 electrons are going to be used in these specific bonds which we have seen. So this implies that the 2 hydrogens are going to be simultaneously bonding to the borons and forming a bridge which I have mentioned. And of course we have said that this specific bridge is going to be using the 2 electrons which are going to be shared among the 3 atoms as shown on the board. Now in this specific of course case, then therefore we're going to see that boron is going to be forming the unique kind of bonding which we are of course expected to be similar to this analogous alkane series member, but of course it's going to be using those 4 electrons to be used in bonding, and that's going to be one of the characteristics of the boron which we're going to see that is going to differentiate it from other elements. And of course we have just talked the concept of dimer, which we are going to look at especially in our discussion of aluminium, especially the formation of the chlorides or the halides of aluminium. We're going to see that there's going to be some of the properties which are going to be formed. And I'd say that basically apart from other elements, boron is going to be displaying unique characteristics of non-metals. So in this case we shall as well mention the concept of aluminium when we shall come to discussing about this specific element, and that's going to create for us a contrast between the 2 as I've said. So kindly check our description boxes for various links of other similar videos. So in our next discussion, we're going to look at the concept of aluminium, gallium, indium, and thallium in that specific order for the group 3 elements. So that is it for now, guys. Bye. God bless you. Catch us in our next video.